So, good morning, one and all. I am Dr. Bharati Sagi, an assistant professor in the Department of Electronics and Instrumentation Engineering, VIGNAna JYOTHI Institute of Engineering and Technology. So, today we will be learning modeling of dynamic systems. It is a part of the Industrial Process Control Instrumentation course, and this is it's a core subject to our instrumentation students, and anybody who is interested in modeling, regulation, automation, robotic applications, this is a very core subject to them. Then moving on, so dynamic modeling of first order and second order process is what we are going to cover under this particular presentation, and we will be looking into the details of first order tank modeling, second order modeling, and interacting and non-interacting subsystem models under this presentation. And any engineering systems that we see in a real-time world, like drones controlling its altitude, or any industry, chemical industry, there is a flow regulation of any chemicals flowing through the plant, and there is a temperature regulation, there is a heat regulation, pressure regulation, and any robotic applications where arm of the robot has been regulated as to pick and drop any, position its arm to pick up and drop any particular object. So in all these applications, there is at the back end there is a automation going on. So in the automation applications, it is a mandate it's a mandatory understanding that there is a sensor to measure what is that it has to automate. So what is the objective for automation, and accordingly it will select a sensor and it will measure all the variables needed from the plant or the process or a system that it is targeted at. And then depending on that, there is a modeling applied to understand the characteristics or the behavior of any given system or a process. So this and once the model is available, it will give us the understanding that what are the characteristics of that particular process or a system. And if you know the characteristics of the system, then we will understand what kind of analogy, what kind of controlling analogy can be applicable, so that in a closed loop control there is a precise and accurate regulation can happen. So now, getting into the details of the order of the process, because the order of the process is important, vital understanding that whether when you would drop down all these heavy systems, chemical plants, plant-wide control, or drone controlling, or robotic controlling, any huge applications, if you bring it boil down to a smaller brick. So this is what we look at is modeling. When it comes to modeling, dynamic modeling, or trying to understand how these variables, how different variables of the process are changing with respect to time, that is nothing but dynamical modeling or transient response understanding. So these systems, all these real-time systems or any complex system can be boiled down or approximated to a first order or a simple second order system models. So order of the system, here we indicate that any differential equation of order 1, it's a differential equation of order 1, can be named as a first order differential equation, will represent a first order system or a first order system model. And then similarly, if the differential equation having a highest order of 2, then it is a second order system model. So depending on the order of the system, we'll also can interpret this physically by looking at how many accumulating or mass or energy accumulating system does the system contain. If it is a tank or a level process we are looking at, if the level process is having one mass accumulation body, then the order of the system would become 1. That is, it is a first order system model. So it is a easy and convenient way to understand and assess any given system as a first order or the second order system, or some combination of these two, or by adding some dynamic response also in terms of process lag. So also gives the overall understanding of the system behavior. So when it comes to first order systems, so generally first order systems are represented in this manner. It's a linear time invariant system model. So where we have a first order differential equation, then we have a time constant parameter tau and a gain parameter k. So here u of t is representing the input to the system. That is, generally in every modeling applications or control applications, we will be observing what is the cause and what is the effect, which means effect will be what the system behavior. So once it receives some sort of cause or some sort of triggering has happened, some sort of initiation or input energization has happened, that will be a cause. So that is represented by U of t, and the response toward the system's response towards the input U of t is given as Y of t. Okay, so in general, in process control applications, we term them differently, a controlled variable and a manipulative variable. So controlled variable is something, the effect of the system, and U of t is the manipulative variable or the input to the system. So if input and output of the systems are given an equation in the first order equation, then it would look something like this. This is a linear time invariant system model, and where k and a time constant tau are the two important parameters that will make us understand how the system is going to behave. The process gain k will give us the understanding that given a U of t input, the system is going to reach to a final steady state value that is a multiply of k. So k times of the input, it will reach the steady state value, and then time constant will tell us so dynamically how the system is going to respond from initial state to its final value. So while traveling from the initial state 0 in this particular case and reaching to a steady state value at some final value k times u value, and in between what is happening, so that time response is dynamic response is given by tau value. So here in this case we observe that depending if the lesser the time constant value, response of the first order system will be faster, and as the time constant value keep increasing towards 7 here, so we can see that there is a sluggish response, right? So the system responds and reaches its final steady state value very slow. Okay, so this is the system characteristics defined by its gain value k value and the tau value. So first order systems, in all first order systems, the response is smoother. So that is from the travel from initial state to the final state is smoother, and there is no oscillations or dynamic, there are no peak overshoots and all, there is no oscillations. But the time constant, due to the heavier or lesser time constant value, the system behavior becomes slower or faster. Right. So in real-time examples for first order systems is drone altitude adjusting slowly to motor thrust lag, or thermal systems, heater tanks flow through a single tank with a constant regulation. So all these can be considered under first order systems. Moving on to the second order system, as we discussed earlier, the order of the system, if it is a second order system model, the differential equation, the order of the differential equation is 2 here. So highest order of differential equation is 2 here. So that is the reason why it is termed as second order system. So in this case, analogously, when you are looking at the physical system, any system which is having at least two accumulating devices, mass accumulating devices or energy accumulating devices, that can be approximated to a second order system model. Okay, in this particular case, we are going to look at the parameters omega n and zeta values. These are the two important parameters which are going to decide the behavior of the second order system, and where y of t is the again our output controlled variable, and u of t is our input or manipulative variable. So depending on the zeta value is a very key here, because depending on the zeta value, whether the final response of the y of t with respect to u of t is whether oscillatory or whether it is critically damped or over damped. So critically damped means when the zeta is equal to 1, so the system response would something look like this. The response is faster and no oscillations and comes to a steady state value sooner. And when it is over damped, the response is sluggish, reaches the steady state value slowly and comes to a steady state value. Okay, when it is under damped, so when the zeta value is less than 1, then there will be an oscillations observed at the response. The system oscillates before it reaches the steady state value. So these are the three important characteristics of a second order system depending on the zeta value. So depending on this natural behavior of the system, we have to decide which kind of controlling, what parameters of controllers are suitable to make the system regulated smoothly. with the required precision, required accuracy, required robustness, depending on the requirements or objectives for the controlling, we have to decide what kind of controller is suitable. So to make such a decision, we need to know what is the model of the system. Whether if it is a 2 accumulating devices, then we'll go for second order system. If it is a 3 accumulating device, accumulation means here we are terming mass accumulation or energy accumulation within the system. If there are 3 accumulating devices connected in sequence, then it will be a third order system, and so on. Okay, now in the course we will be limiting ourselves to modeling first order system or a second order system, because we assume that any real time application can be dropped or approximated to any of these first order system or second order system with a delay can be approximated. And if if we can reduce the order of the system, the controller designing also becomes convenient, and the regulation and maintenance also becomes convenient. So generally second order systems will be much more precise compared to first order systems, and the examples include robotic arm with inertia, spring mass damper mechanism, or pressure in a hydraulic line. All these comes under second order systems. So now mathematical modeling, understanding what is mathematical modeling, why do we need to discuss this? So recalling all what we have discussed so far, mathematical modeling is a process of representing a real physical system using mathematical equations or simple structures to understand, predict, control its behavior. So in simple terms, given any system, any process you take, whether it is a drone, whether it is a chemical industry or a tank level control or a flow control or any kind of regulatory operation that you are looking at. So we understand that every process or a system has some input which has to be converted into a corresponding response. So input we are calling as U of t and output as Y of t. So U of t can also be a cause, can be called as a cause, and this is an effect. So this U of t in our IPCA, generally we call it as manipulative variable MV, and Y of t as controlled variable CV. So this is what we are going to measure using a measuring device to continuously understand what is the behavior of the process by looking at Y of t. And so now, mathematical modeling is nothing but finding out the relationship between Y of t and U of t. And this can this can be done in various ways. Generally we use transfer function models or state space models or polynomial representations or mechanistic type of nonlinear models and data driven models, gray box modeling and fuzzy modeling, and there are many other varieties also have come into picture recently. So in our coursework we will be looking at these transfer function models which are built from the conservation laws. So law of conservations or law of accumulation. So each system is capable of accumulating some sort of mass or energy. Depending on that principle, we will be extracting the mathematical representation or relationship between the manipulative variable and the controlled variable. So here in this course, we will be looking into the details of building transfer function models, and other types are also important, but right now it is not under the scope of this particular course. And moving on, so let us start with a simple example, how to build a mathematical model for a first order tank level system. So here we can observe that this is a tank, there is a rectangular tank, or we can assume this is a rectangular or a rectangular or a cylindrical tank, where the area of cross section of the liquid at any given height is constant A, and there is an inflow Q of t and there is an outflow Q naught of t. So both are functions of time again, and H of t is the height of the liquid in the tank, which is varying with respect to time. Right. So these are called process variables. This is one process variable, another process variable, and another process variable. So these are three process variables we are looking at in this application. In case what if I want to regulate this particular process? So, and I have a restriction at the outlet. There is a valve arrangement at the outlet with a restriction coefficient R. So now let us write down what is Q of t. Q of t is the inflow rate, Q naught of t is outflow rate, and then H of t, height of the liquid in the tank, and A is the area of cross section of liquid. It is not of the, so liquid is being contained within the tank. While regulating the liquid, we also have to look at the area of cross section of the liquid at different heights, and height of the liquid in the tank, and the other two parameters, inflow and outflow. So conservation law states that rate of accumulation, mass accumulation or energy accumulation, is equal to mass or energy inflow to the system minus mass or energy outflow from the system. By using this particular simple conservation law, we can build mathematical models. This kind of modeling is also called as first principle model. So this is also called as first principle model. Right. So how do we apply this conservation law to this particular tank problem? So we know that rate of accumulation here in this sense, so we are looking at volumetric mass accumulation within the system, that is volumetric fluid that is being accumulated within the tank, which means this can also be expressed as d volume of liquid in the tank by dt, dV of t by dt. So we know volume of the liquid in the tank can be expressed as d times A H of t by dt, where we know that A is a constant because it is a rectangular. For a rectangular tank, A is constant. So A, area of cross section, is constant for rectangular or square tank. So at any given height, the area of cross section of the liquid will be same. So that is why we have considered A as constant. So this becomes A dH of t by dt. So there is only one variable which is changing with respect to time, that is H of t in the tank. Right. So how do you apply? So now we know that rate of accumulation, that mass accumulation in the tank is equal to A dH of t by dt, which is equal to mass inflow to the system is, here in this case it is Q of t, minus mass outflow from the system is Q naught of t. So while building mathematical equation, understanding what is the controlled variable and what is the manipulative variable is very important for any given system. We know that the objective for the system is to regulate the water in the tank. So whether the liquid level has been maintained within the tank is attained or not is understood by looking at H of t. So this is the primary controlled variable. So this is the controlled variable and this is the manipulative variable. There are ways of identifying what is a suitable manipulative variable. So generally what we prefer is, if you have a set of process variables, as we already termed that this Q of t, Q naught of t, H of t are considered to be process variables, out of which we already know that H of t is a controlled variable, because this is what is defining what is whether the system is regulated or not is observed by looking at H of t. That is why it is a controlled variable, and any other parameter other than controlled variable can be a possible manipulative variable. So we will be left with two more variables, Q of t and Q naught of t, out of which we try to see a variable, process variable, which has a direct impact on the controlled variable, and another one is whether if that particular process variable is it independent of the other variables. So we are looking at an independent process variable, and it should have a direct impact on controlled variable. So out of Q of t and Q naught of t, we can observe that Q of t is an independent process variable which has a direct impact on the H of t. So therefore I will select Q of t as my manipulative variable. But selection of manipulative variable also depends on the various other cases, various other requirement of the closed loop controlling, but that depends on the particular case. But generally we will look for variables, process variables, which are independent of other variables. So this q of t is independent of other variables, therefore I have selected as manipulative variable. Now this is my cause, that is, if I change q of t, there is a considerable change observed in h of t, controlled variable. So that is the reason why we have to build a mathematical relationship between h of t and q of t. So this mathematical model that we are going to build is going to give us a expression in terms of S domain as output h of s by input q of s, which means effect by cause. So this is the relation we are going to identify after the end of this modeling. Right. So coming back to the equation conservation law that we applied here, a dh of t by dt is equal to q of t minus q naught of t. So here in this case we already learned that this is independent, we don't need to change its identity, but we know that q naught is a dependent variable because it is directly dependent on height of the liquid in the tank. So if the physical understanding is known, then q naught of t can be expressed as, if it is a laminar flow, it will be expressed by h by r, height of the liquid in the tank h of t by r for a laminar flow. If the liquid flow is laminar in nature, then q naught of t is equal to h of t by r. Otherwise, it would be root of h by r if it is a turbulent flow. Simple liquid level systems and all, generally it is assumed to be a laminar flow, and the relationship between this q naught and h will be linear in nature. Otherwise, if you are considering a turbulent flow, then we have to consider root h of r. For now, we will be considering a laminar flow. We are looking at a linear model expression here. So we will be looking at q naught of t expressed as h of t by r. So I will be substituting 2 in 1. The 1 becomes a times t h of t by dt is equal to q of t minus h of t by r. So now we will rearrange this particular equation. This becomes ar dh of t by dt is equal to r times q of t minus h of t. So I will bring all the h of t parameters to the left. This becomes ar dh of t by dt plus h of t is equal to r times q of t. By applying Laplace transformation for this linear first order differential equation, we will get ars h of s plus h of s is equal to r times q of s. So we can take h of s common and bring the q of s over here. It becomes r by ars plus 1. So now we can observe this is a first order differential equation with the gain r and the time constant a into r. So now it is analogous to the first order system representation as k by tau s plus 1, right? So if the system has this, we already understood that depending on the time constant value and the gain value, by looking at gain we understand for a step, this is a step response equation for the first order system, and where k is the gain of the system. So depending on how much input you are giving, let us say if you are giving u times of the step input, then y of t would be the final value reached by y of t from its initial value 0 would be k times u value, and this is the final state reached by our response h of t. And while reaching to its final steady state value, it may take this path, or it may take this path, or it may take this path. So depending on the tau value, so these paths will depend on what is the value of tau. If it is tau 1, this is tau 2, tau 3. If tau 1 is lesser, so larger the time constant value, sluggish will be the system response. Smaller the time constant value, faster will be the response. But in any case, we understand that first order system does not oscillate. So it is very convenient to handle these kind of systems, and if there is a possibility to approximate any given system as a first order system, so designing closed loop controlling will be much convenient. Okay, with this we try to sum up what we have learned so far. We have seen that every real-time system can be expressed as a simple first order or second order dynamic system, and by understanding any system in terms of an order of the system, then it is easy to understand its behavior, to predict its behavior, dynamic response, and also it is convenient to apply any controlling that we want to do. So whether we want to apply PID controlling or MPC controlling in the fourth going, then it is very convenient, flexible to apply controllers if you know the characteristics of the system in hand. So for that we will be building models. Building models is nothing but finding out the relationship between what the controlled variable and the manipulative variable. So the manipulative variables and controlled variables are selected such a way for a system that if you know the objective for the process, for example in the liquid level system that we have understood earlier, so if the objective is to regulate the liquid level in the tank, it is understood by looking at the height of the liquid in the tank. So that is a primary controlled variable. And secondly, the height of the liquid in the tank can be regulated by using either by input flow Q input or output flow Q naught. So either of these can be selected as a manipulative variable, but generally we tend to select independent variables or as manipulative variables. So in this particular case, it is Q of t. So we are trying to build the relationship between the manipulative variable Q of t and the controlled variable H of t by using a first order conservation laws. We have applied a rate of accumulation is equal to inflow minus outflow equation to derive the relationship between the controlled and the manipulative variables. So we have seen the procedure, and depending on the expression, the outcome of this modeling procedure is we are going to get a first order representation in the form of k by tau s plus 1, where k is the gain of the system and process, and tau is the time constant of the process. For a liquid level system, we got R by ARS plus 1, where R is the gain of the system, AR is the time constant of the system. So time constant will decide what is the how dynamically the system is going to reach its final steady state value. So that's all for today's session, and moving on we'll be learning about second order systems and different subsystem understanding, modeling of the second order systems as interacting or non-interacting systems in the next sessions. Thank you.
Like, share, comment, and subscribe VNR Digital Learning Resource YouTube channel.